radical experiment takes aim at global warming. The payload? The world's thinnest lenses. The ultimate mission is inconceivable. Deflect 2% of the sun's rays away from Earth to save humanity from runaway climate change. It's called geoengineering. But can this radical science really work? A special discovery team will search for the answers. The clock is ticking. It's time for action.
This episode of Discuss is presented by Bank of America.
The power of the sun is the source of all life on our planet. Now, this force has become a threat as global warming traps more and more of the sun's heat with potentially disastrous effects. But what if you could slow down climate change and turn down the power of the sun? A world-famous astronomer in Arizona thinks it's possible. And his name is Roger Angel.
If you reduce the solar energy by about 2%, then that's enough to take Earth's temperature back to pre-industrial levels.
Roger Angel's plan is a mind-bending application of geoengineering, a sunshield in space. The Sunshield is a huge cloud of 23-inch diameter lenses. They'll be launched to a spot 1 million miles from Earth, where the gravitational pull between our planet and the sun is canceled out, keeping the lenses in position.
What the lenses do is that they transmit the sunlight, but they bend it a bit, so that instead of hitting the Earth as it otherwise would, it's just deviated a bit to one side.
Solar-powered positioning devices attached to the lenses keep them evenly spread apart. As a whole, this network acts like a shield 1 million miles square, deflecting just enough sun, 2% worth, to counteract global warming. But the costs of sending masses of thick, heavy glass lenses into space would break the world economy. Roger Angel needs to create super light, affordable lenses and run experiments to find the best way to get them into space. He's asked a special discovery team to analyze the theory, the technology, and the economics of the space sunshield.
Look at this thing, it's absolutely fantastic.
That's massive.
Welcome to the LBT, Large Binocular Telescope.
So you want to offset global warming by putting a big sunshade up in space?
Basil Singer is a quantum physicist.
If Roger Angel's concept makes sense scientifically, then we need to help him devise some experiments so he can progress.
So, Professor, you're talking about a lens or a sunshade 1 million square miles in size?
Kevin O'Leary runs a global business empire.
To make a case for the sunscreen, I need to weigh the costs, literally against the future of the planet.
What I'm hearing is I'm hearing million square miles and millions of tons, so I'm seeing this giant pair of sunglasses.
Jennifer Langwell is a leading eco-construction designer.
There are still immense engineering challenges that we face if we're going to try and get lenses into space.
The first goal is to find out if Dr. Angel's research has led to any hard results.
Have you manufactured such a lens yet?
Some while back, I manufactured the sort of critical part of the lens, which is the way you shape the surface to make it scatter the light.
Angel has actually built a glass refractor
It should be pretty transparent.
and filmed it at work. It's a thick piece of glass covered with a pattern of micro-engineered holes. Held in front of a laser beam, it bends light the same way a lens could deflect the sun's rays in space. But there's a downside.
How many would we need to get into space?
16 trillion make up the million square miles. that you
16
want.
trillion.
Right.
The cost of sending 16 trillion glass lenses like this one into space would top $1.4 million trillion and bankrupt the world economy for centuries.
So far, we've only made it on a thick piece of glass. The step we need to take now is to see if we can make the same diffracting surface, but now on an incredibly thin film.
Angel's heavy glass has a 2-inch edge. What he needs for a Sunshield lens must weigh less than an ounce and measure 1 micron thick, or 1/50th the thickness of a human hair. The team faces 2 major challenges. 1, make the thinnest, lightest lens the world has ever seen. 2, create scaled-down experiments to test the best way to get the lenses into space.
Roger Angel's concept of the space sunshade really hinges on the lenses. As far as I know, nobody has ever made lenses anywhere near as thin or as light as the ones we need. It's a huge challenge, but I've got some leads.
Basil heads for Holland to a special lab willing to take on the challenge.
I think that the best bet for making an ultra-thin lens is the lab at the Delft Institute. The scientists here specialize in making silicon chips and wafers, and I'm hoping they can use the same technology to make sunshade lenses for our tests.
The experiments here are so sensitive, a speck of dust could ruin a week's worth of work. Basil's come to see Dr. Gleb Vadovin, one of the world's foremost chip engineers.
Hello. Hello. You should be very careful with your movements because it's dust-free. We are afraid of dust. Take a seat.
Okay, I'll sit down.
The future of the Sunshield comes down to one question. Can Dr. Vadovin take a sliver of silicon and turn it into an ultra-thin sun-deflecting lens? That's the plan.
If it's in
But
scale,
Vadovin isn't buying it.
So you want to have it on a very thin film?
Yes.
No, I don't think it's going to work.
If we can't print this onto 1 micron thick material, the whole experiment is down the pan.
Dr. Vadovin wants to scrap Angel's lens and create a stronger, thicker one instead.
Up into space.
But Basil knows a thicker, heavier lens will cost far too much to launch into space.
It's up to you. Right now, you need to make a choice between the original design of Roger Angel and alternative design from us.
I know you're the expert in this field, and you think that you could make a design which is structurally more solid, but I think I'm going to have to go with Roger Angel's initial design.
Dr. Vadovin finally gives in. He'll follow Roger Angel's plan for a scale model lens 2/3 of an inch in diameter. While Basil leaves the lab, the engineer goes to work. Vadovin heats a silicon wafer to a temperature of 900 degrees Fahrenheit in a stainless steel oven filled with ammonia gas. The heat causes the ammonia to react with the silicon to coat the wafer with a thin film of silicon nitride. A layer of photosensitive material is added to both sides of the wafer. A pattern of holes is then projected on the disc, which causes a chemical reaction in the photosensitive material. Streams of ions are accelerated onto the wafer, eating into the design and creating the final pattern of holes. Each silicon wafer holds 12 lenses, and now there's only one more critical stage to go. A chemical solution dissolves away the photoresistant material, creating the finished lens. If the experiment works, the data could help scientists manufacture mass quantities of Sunshield lenses in the future. But for now, creating lenses is just half the battle. The team will face a series of radical experiments that will test their nerves, along with Roger Angel's Sunshield.
So we have no picture of the lenses? No picture. You've got to be kidding.
A high-tech strategy that could buy the world some precious time. If global warming melts the world's ice caps and glaciers, sea levels will rise 260 feet. Just a 12-foot rise would flood 9,000 square miles of Florida permanently. Roger Angel wants to prevent disasters like these by cooling the Earth with 16 trillion sun-refracting lenses. In Holland, silicon engineer Gleb Vadovin finishes work on the first prototype Sunshield lenses. Discovery team's Basil Singer rushes back to see the results. The lenses, called membranes, are done, but how many will survive?
Come here, look. So at this moment, everything gets extremely fragile.
I can see a large hole in this one.
Well, yeah, well, probably this membrane will break soon.
So this one's going to break.
Yeah,
So that's 1 out of 10 that we know now is probably going to break.
Probably. Well, probably they all will break. I don't know, but
The lenses are so thin, they could break just being removed from the solution.
we are going to break them. Yeah. So we are going to break this wafer without breaking the membranes.
6 out of 10 silicon nitride lenses make it. But will they work?
So we're going to test it with this laser pen.
Yes.
I turn the light off down here. Ready?
Okay. Yes.
So now we have a single spot.
Yes.
And if we put this in the way, we should see a diffraction pattern.
Yes.
Please. Whoa, look at that.
The team takes the Sunshield a giant step forward with an ultra-thin lens that's just what the doctor ordered.
That's the thinnest lens ever made.
What we've done in this project is make the very first material which is specifically engineered to do this job of deflecting sunlight to cool the planet.
They work. Thank you so much.
It's now time to confront 2 issues. Can a Sunshield lens survive the stress of a launch into space? And just what technology could get them there in the future? Conventional rocket systems are expensive and polluting. But Professor Angel thinks a revolutionary breakthrough in space travel could be available in roughly 30 years. It's called a coil gun. And fires projectiles with such deadly speed, the military hopes to develop them as superweapons. Angel's plan calls for 20 coil guns to be built around the world. Buried in mountains, their 3-foot diameter vertical gun barrels are over a mile long. Projectiles filled with Sunshield lenses are fired using huge blasts of electromagnetic energy. A series of wire coils running up the length of each barrel are rapidly charged, then discharged in sequence, attracting then repelling the projectile, accelerating it along the barrel until it blasts out of the gun and into space. Each projectile carries 800,000 lenses, but in order to escape Earth's gravity, the coil gun must accelerate the projectile to over 25,000 miles per hour in just the length of the barrel. This enormous acceleration will exert massive stress on the fragile lenses. Dr. Angel needs to know whether they could survive. So Basil's mission now is to see if this future technology could be tested today.
It's not easy finding someone who's going to build me a coil gun. Apart from the military, not too many people are involved with developing coil guns.
Basil's come to a testing ground not far from Roger Angel's observatory. It's run by weapons designer Todd Tadashini, who's building the team a scale model coil gun.
Hello, Todd.
Ah, good to meet you at last. How you doing?
Let's see the plans.
Okay.
The experiment has 2 goals. 1, measure the coil gun's forward acceleration. 2, see if the lenses could survive a launch in a coil gun projectile.
The essential thing is that this can accelerate our projectile on extremely thin lenses.
Up to the kind of conditions that it's going to be under when we try and get it out into space. And those conditions are about 1,000 G.
Todd's got his work cut out. 1,000 G's acceleration is equivalent to going from 0 to almost 22,000 miles per hour in just 1 second. Fast enough to escape the gravity of the Earth.
Nobody's done this before. Right? Nobody has done what we're trying to do before.
The key to the coil gun's power are special devices that store energy. Called capacitors, they hold a huge charge of electricity. When it's released, it powers the projectile out of the barrel with instantaneous force.
We've got 140 capacitors in there. Each one will kill 50 people if you touch across the terminals.
This scale model projectile will carry the lenses in a violent launch.
You've got to release that power in absolute milliseconds, just fractions of a second.
Tomorrow morning, the coil gun could point the way to the future, or turn into a costly dead end. While Basil and Todd waited out, Kevin and Jennifer began a countdown of their own a continent away.
Whoa, that's Apollo 11 right there. That thing will take us to the moon. Look at this. Beautiful.
We're not going to know if the lenses survive.
Where is the picture of the lenses?
If cuts in carbon emissions come too late to stop global warming, 50% of plant and animal species could disappear by the end of this century. To save them, Roger Angel wants options like the Sunshield.
So under those conditions, it's worth thinking about whether we got some insurance policy. And the one thing that we can do to prevent the Earth heating up is to reduce the amount of solar energy arriving at the Earth.
A key part of Angel's insurance policy is powered up in Arizona. A scale model of a coil gun. The jolt of electricity, enough to power 5,000 homes for a year, must accelerate a capsule at escape velocity. It's a key goal if Roger Angel's vision of a cheap, effective launch is ever to become a reality.
For the first test, we're just going to test the gun and look at the kind of acceleration that we can get up to. So we'll load it without the lens for now.
That's it.
What sort of power do you get out of this thing?
Well, it's running about 10,000 joules. For the millisecond or two that this thing is actually shooting, that is enough power to run a city.
Where's the acceleration readout?
That's in the firing box, so it's all there when you're operated. You've got your firing buttons and whatnot, and you've got your G-force meter here.
Oh, very easy.
Weird-looking stuff.
Todd and Basil must make their first shot into a block of ballistics gel. The gel should let them recover the projectile undamaged to use for more tests.
Whoa. Okay. When we get to charge, we're not going to be hanging about, okay? So I'll let the world know that we're ready to go. I'll give a countdown, 5 to 1, and then we go for it. Charging!
The capacitors are fully charged. When Todd flips the switch, 2,000 volts will surge into the gun coil in a millisecond. The massive jolt should accelerate the missile from 0 to 100 miles per hour in the span of just 2 inches.
Firing! 5, 4, 3, 2, 1!
The gun has fired, but has it passed the vital test? Basil needs to know the force it has generated.
And what's the G-force on that?
You know what that means? Do you know what?
1,126!
That is, put it there, man.
Brilliant.
Result.
That's amazing. So we can do over 1,000 G.
You can do over 1,000 G.
The coil gun works. And at 1,000 Gs, it's proof that Roger Angel's vision of a giant gun could provide enough force to escape the Earth's gravity. But there's a problem. The acceleration was so great, a piece of projectile was jammed into the payload chamber. If the lenses were inside, they'd have been crushed.
That is not good news.
The damage is caused by a shock wave passing through the projectile at 1,000 Gs, pushing a column of carbon fiber into the payload section. When Professor Angel gets the test results, he arrives with a solution.
I think if we were able to test this in vacuum, that would at least get rid of all that air shock coupling there.
Yeah. That is a brilliant idea. Vacuum.
Yeah.
We can do it. Yeah, no, it's a good idea. If we build a little chamber that sits right on top of here, so it's the same size as this, and it just sleeves right inside the outer body of the projectile. So we just pop it on, and then push it up there.
Todd's team creates a vacuum chamber. Every molecule of air inside it will be sucked out. Angel's solution is simple. Without air, a shock wave has nothing to shock. 24 hours later, the vacuum chamber is installed inside a new projectile.
And here's the housing that the lens is going to go in.
Okay.
That slots into there.
That's the one.
Ready? Let's do it.
Okay.
The coil gun is fired vertically this time to put maximum stress on the lenses.
Okay.
A parachute will take it down to Earth to see if the lenses survived.
Great.
Okay. Yeah, that's good. Right, we're ready to do it. Charging! And it takes a while to get that power in there. We've got 200 volts in all 4 banks now.
This is it, guys.
Firing in 5, 4, 3, 2, 1, fire! Watch yourself. Watch yourself.
The high-tech gun works perfectly, but the experiment is ruined by the failure of a low-tech parachute.
That's taken some serious impact. Right, let's get that lens out and see if it's still intact. It's completely disintegrated.
Well, I think that's telling us something. It's not the fragility of the thin membrane.
The team will never know what broke the lenses, the G-force of the launch or the impact with the ground. But Professor Angel thinks in either case, the lenses could have survived if the frame supporting them had been stronger. He believes the massive G-forces actually bent the supports, causing the lenses to snap into pieces.
My reading is we have to support it very carefully around the edge. Well, we made good headway with the gun, right?
In spite of the setback,
we exceeded my expectations by making the world's thinnest lenses, and we managed to accelerate them to 1,000 G using a coil gun. The parachute problem, that can be sorted out, but what we've proved is that this system works.
in the meantime, there's only one other alternative. And it's time to check it out. Solar energy equal to 125,000 atom bombs hits the Earth every minute. CO2 in our atmosphere traps the heat, and the warming effects could linger for decades, according to astronomer Roger Angel.
The lifetime of carbon dioxide in the atmosphere is a century or more.
Giant coil guns could launch this Sunshield to return global temperatures to normal. but timing is crucial.
While the coil gun looks like the answer, what if the technology just isn't ready decades from now when we need to launch the Sunshade into space? The only other technology available right now is rocket power.
The team finds a rocket maker in England willing to take on a complicated project with a hard deadline.
There's huge amounts of risk in this technology. To actually lift Roger Angel's lenses into space, not only the risks are huge, but also this rocket may be very difficult in terms of its costs.
The price tag runs a poor second to the main issue. Can the delicate Sunshield lenses survive the stress of a conventional launch? Even a scaled-down rocket will cost nearly $200,000. But the engineers here in Northeast England are confident they can hit the experiment goals.
Hello.
The design group is led by Damian Hall and Colin Rowe.
Can you design and build a rocket that can mimic a launch into outer space?
We can do that, Jennifer, but the problem you have is the forces on those lenses are going to be massive.
The G-forces from the vibration are much greater than I anticipated. We're looking at about 25 Gs, which is enough to shake apart a car.
While coil guns accelerate their capsules at extremely high speeds, the ride is almost vibration-free. Rockets are another story. From takeoff to escape velocity, the engines will rattle and shake the payload in multiple directions, each with a force of 25 Gs. Inside the payload section, onboard cameras will monitor the stress on the lenses. They'll experience the worst punishment from launch to 11,000 feet. That's where the experiment ends and the engines shut down. Next, the payload section separates, and the lenses return to Earth to be checked for damage. Jennifer will also design an onboard camera system to monitor the lenses during launch. Within days, Damian assembles a frame for the solid fuel motors. The completed rocket will stand almost 50 feet tall and reach its maximum altitude in just 25 seconds. Jennifer's moved the experiment a giant step ahead by designing a shock-proof cradle for the lenses.
We put together this system of springs with gas shocks so that regardless of the force and the direction, the lenses would be secure. I have a lens holding device here that I'm looking at mounting the lenses in. Goes right inside here.
Excellent.
2 cameras for monitoring the lenses. I'm hoping that this is going to keep my lenses safe.
Rocket construction is almost complete, and morale is high. Jennifer and Kevin head for the British military base at Otterburn. The base commander has given the team access to a decommissioned launch pad for the experiment.
I have never seen a rocket launch. I'm very excited about this. Where is she? Whoa, that's Apollo 11 right there. That thing will take us to the moon. That is beautiful.
Just 2 minutes, James.
Damien,
God,
how are you?
look at this. Beautiful.
The world's thinnest lenses, created in Holland, will soon become the payload in a sturdy English rocket. The stages are made of trilite aluminum, a tough, flexible metal. 21 motors will burn 300 pounds of rocket fuel in 15 seconds, producing 10 tons of thrust. Enough to accelerate an automobile from 0 to 100 miles per hour in 2.1 seconds. Fully assembled, the rocket weighs 1,100 pounds and stands as tall as a Scud missile.
If we can prove that the lenses will survive a conventional rocket launch, even if we don't have a coil gun available or ready, we can still prove the theory that we can get the lenses into space. It's not an ideal solution, but it's more important to get the lenses into space than how we do it.
The amount of reduction in global warming you get from the launched material is so high that
even if you had to burn carbon to launch the Space Sunshade, that would be a good choice.
If this was a full-scale launch of the Sunshield, a future rocket would have to be massive. To deliver all 16 trillion lenses into space would require one liftoff every 20 minutes over a period of 6.5 years. A weather window has opened, and Damien's crew have begun to pre-launch the rocket. Some of the rocket engines use liquid fuel. Because it's so volatile, Damien's team fills the tanks just 10 minutes before launch. From this control room bunker, Jennifer monitors the onboard cameras trained on the lenses. But the live feed from the rocket has suddenly gone down.
We have a remote camera feed, which I am desperately trying to get working, because if we don't have this live feed and something happens, we're not going to know if the lenses survive. So I think that we're running up to check the equipment up top that's transmitting. We might get a signal shortly.
Nothing.
Oh,
what's this? This looks interesting. Those are the lenses.
We're getting some form of picture, but it's very, very sketchy, and it's black and white. Over.
But look, we can't launch this if we can't see these things.
Getting colour intermittently. It keeps coming and going. Over.
It's too late to fix the cameras. Stopping the launch means draining hundreds of pounds of highly explosive fuel.
Where is the picture of the lenses?
Yeah, we're not going to have a picture of the lenses.
You're joking.
No. And apparently there's been an issue with the batteries in the rocket.
So we have no picture of the lenses?
No picture of the lenses.
But Jennifer has installed a backup system to the live feed. The cameras have memory cards to record how the lenses perform over the course of the launch. Damien and the ground crew make a quick retreat to the bunker. Filled with nitrous oxide and solid fuel, the rocket is a potential bomb. Professor Angel's high-tech proposal has suffered from a series of low-tech failures. But confidence at the bunker is high, and all systems are go.
We are bringing the countdown forward.
Pray it does not explode. Payload, you're intact.
Silence, please. 9, 8, 7, 6, 5, 4, 3, 2, 1.
Engines brimming with explosive fuel are about to blast a rocket to 11,000 feet in less than 25 seconds. The payload, a set of delicate lenses. The mission, prove the Sunshield could survive rocket launch vibrations. The hope that geoengineering can save humanity from climate change.
5, 4, 3, 2, 1. Ignition.
As the rocket reaches full acceleration, onboard cameras will record the stress on the lenses. But something's gone wrong. The main engine stutters, then reignites.
Go!
At 3,000 feet, the motors fail.
Come on! Come on! safety officer. No one is to approach the area. Everybody listen to me. Everybody listen to me.
Catastrophic failure.
One or two vehicles going down towards where the rocket went down. Nobody else is to approach the rocket.
I saw no flames. I saw no smoke.
There was no ball of fire.
If the onboard camera footage shows the lenses survived the launch, the experiment is a success.
One wreckage. That's the whole rocket, Damien?
That's the whole rocket. Right there. That's it.
Where would the lenses be?
We don't know until we dig them out, if we can find them.
They gotta be in there somewhere. That's incredible. It dug itself its own grave.
Yep.
Lift this stuff out. Let's see if we can find them alive or not.
Carefully, guys. Disconnect the rear of the chute and get some more.
Real-time computer data pins the cause of the crash on a 2-second firing delay in the second stage motors.
Camera.
I see payload. We're close. We're close.
Damien, you see anything that looks like lenses?
We're not far off. We can see springs.
Underneath all this is your lens.
It's unlikely the lenses survived the violent crash.
That's the bottom side of the holder.
You got it?
A little bit.
All this stuff, those are pieces of lenses. See the shiny purple?
Vaporized. Vaporized.
Kevin and Jennifer can only hope the lenses manage to withstand the G-force of the liftoff.
All right, what's up, guys?
Whoa, what's that?
It's the solid-state recorders.
If the onboard cameras prove that's the case, the experiment is a success.
Grab it. I see it. I see blue. Yes!
We have
One card.
It's intact. It's completely intact.
battery. 6.
Perfect shape.
How many? 6.
Clearly, we need an expert now to go and look at this card and see if they can interrogate the data and pull anything off it. It's not over till we get the data off this card.
Hopefully, the inspection will reveal the crucial images. But for now, the only thing the team can do is wait and hope.
Wait.
Within hours, the team gets the results on the memory card. No images were found, probably due to the damage from the crash. In spite of the failure, real progress was made throughout the course of the experiment. The challenge now is to learn from it, to answer vital questions. If the space shield was launched to that crucial spot between the Earth and the Sun, what would really happen to our planet? Would we save ourselves or squander a global fortune? The experiments are over, and astronomer Roger Angel needs a critical evaluation of his space sunshield. Basil Singer heads for the University of Victoria in British Columbia. Here, researchers have harnessed supercomputers to see if the sunshield could make a difference. Professor Andrew Weaver is a lead author of the latest report on global warming by the Intergovernmental Panel on Climate Change. At Basil's request, he's projected a scenario for the next 100 years based on climate change continuing at the same rate.
As you see, as we start, it's warming everywhere, and by the end of this century, you see it's about 3 degrees warming, with sea level rise a little bit over a foot.
Weaver's IPCC report suggests that by 2020, climate change could cause a catastrophic 50% drop in agricultural production in parts of Africa. And NASA studies show increasing temperatures and rising sea levels put New York City at higher risk of severe hurricane damage. So how much of a difference would the sunshield make if it was operational during the same period?
the movie going from the year 2007. It takes off and it starts to cool, actually, quite dramatically during the implementation period. In fact, it's cooling so rapidly, it's taking us back to pre-industrial temperatures.
So this isn't just putting the brakes on global warming, this is putting global warming into reverse.
That's correct.
If work began immediately, Roger Angel believes it would be possible to have the Sunshield operational by 2040.
Things that take a few decades are not that futuristic. It's not immediate, but at this stage, I think we need to look at all our options.
Temperatures would drop as Weaver's model predicts, but only with a simultaneous and significant reduction in greenhouse gas emissions. Without that decrease, the benefits of the Sunshield will zero out before the end of our century. Climate scientists are just beginning to weigh options like the Sunshield as we look to an uncertain future.
If you were to put in this much effort, maybe we should just be building wind turbines and solar cells and things like that and not bother building these huge satellites. But I don't think it's completely off the charts. I think it's off the charts this century.
What we have to be prepared for is that many of these experiments aren't going to work. This is the way science and engineering progress. You build something, you try it, it doesn't work, you try it again. This is sometimes called learning by doing. We're not doing, and therefore we're not learning.
There's some really interesting questions involved in whether shading the sun will do what you want, other than keep global average temperature down, which would help, but it isn't everything.
We don't really know what will happen to the Earth system. If we change a temperature to bring us back to pre-industrial temperatures, we don't know what other effects we'll have on the planet.
This is a last-ditch effort, because you can be sure that when you do something like that, you cause large, unintended consequences that we only very, very dimly understand. And it is hubris to think that we know enough to do that unless we find ourselves in the soup and we have no choice.
But scientists like Roger Angel view these geoengineering projects as high-tech safety nets we can't afford to ignore.
There are things with climate change that are irreversible. It's worth thinking about whether we got some insurance policy, and the one thing that we can do to prevent the Earth heating up is to reduce the amount of solar energy arriving at the Earth.
The Space Sunshield is just one of many geoengineering alternatives emerging from the scientific community. While the effort continues to cut our carbon emissions, we need to include these massive strategies in our dialogue to make the